we mainly here find the limit of the given function at infinity. See the problem, evaluate limit of cos x as x tends to infinity. You can write that the command for obtaining that limit. That command is given here, limit of cos x, then put comma. You have to write x equal to infinity. Instead of using that infinity symbol, you have to write the complete word infinity, x equal to infinity, and then close the bracket, and then we can now apply this. We can try this command using the Jupyter notebook. In Sagemath. Okay, that's typeset, and it is typed. After that, you can take the output. Yeah, we are waiting for that output. Yeah, we get that the output answer is indeterminate. The value doesn't exist. And then another example here, is given to find limit of cos x by x as x tends to infinity. But directly you can obtain that limit using this command, limit of cos x by x comma x at infinity. First let's try that. After that we'll use another method for approximating the limit. Here the limit value is obtained as 0. So let's check this, check whether this is true using that squeezing lemma. In some cases, we know that in some cases we can apply the squeezing lemma to find the limit of a function. For that, we have to consider two more functions, which one of the function is an upper limit, or it makes an upper limit for the given function. Here the given function is cos x by x, and the other function must be it must make the lower bound of the given function. Here in this in the given example, in the case of the given example, let's find which function can be used as the upper function and which one as the lower function. We can verify by squeeze theorem. By using we can verify the result. The result is the limit of the function is obtained here 0. We can verify this using squeeze lemma. So for that we set a function fx equal to -1 by absolute value of x modulus of x, and gx equal to cos x by x, and hx equals 1 divided by modulus of x. Then we can write clearly. We can write that fx is now less than or equal to gx less than or equal to hx. So as we if the functions are as we defined here, then we can write the inequality f of x less than or equal to g of x less than or equal to h of x. It's because there is a reason, because of the inequality, that -1 is less than or equal to cos x is less than or equal to 1. See, due to this inequality, you can divide throughout the three quantities. So you can throughout that expression by modulus of x. You can divide it by modulus of x, and then you can see that you can see that we can see that after division we get that we get -1 divided by modulus of x less than or equal to cos x by x less than or equal to 1 by modulus of x, but -1 by modulus of x is equal to fx and 1 by modulus of x equal to gx. Sorry, it's equal to hx. 1 by modulus of x equal to hx. Hence you can write, you get that the inequality fx is less than or equal to gx less than or equal to hx. So what we are going to do next is we are going to plot three functions. And the three functions are fx, gx and hx. One by one we are going to plot the three functions. So for that, for plotting the first function, we define g1. First we define g1 equal to plot of the function -1 by absolute value of x, -1 divided by absolute value of x, then comma x 0 comma 10. And this stands for the lower limit and upper limit of x. On that in that limit or between this limit, we are going to plot the curve of the curve of the function. We have to plot this, and also the y values, the lower and upper values of y is given here. Y minimum is -1 and y maximum as 1. And we can use the color green to draw the corresponding curve, and we use size 3. So okay, first let's do that. Let's do that in the system. Okay. There is some error. Okay. Okay, then I am going to change this the quotation. I have to correct that quotation, single quotation green. Green must be inside that single quotation. There is an error in that in that part of the command while we copy it from the text, and some error has occurred. So in order to correct that error, I retype it that part, only that part I have written again. I have corrected that error. So you can now display, if you want to see the display or the figure. If you want to see the figure, you can just type g1, and then after that you can take the output. Waiting for the output. If there is no other mistake in that expression written, then we will get that output. See, we must wait for some time. If there is an error, then the error message will also come, but nothing is now we get that. We have obtained that the curve corresponding to the function written there, and then come back to the material, and after, and we as the next step we copy the second function, and we copy the second function, and we are going to we want to plot the second function. So that is, and that's named, that's given the second curve is given the name G2. So and it will appear in color. So okay, after correcting that, I just type G2 again. I type G2, you know, I want to, because I want to take the output. I want to see the output. The graph G2 will be displayed now. We have to wait. Yeah, first it has to calculate the values, and then the system will take time to draw the figure. Yeah, you can see in red color the curve corresponding to the function cos x divided by, the function is cos x divided by x. Cos x by x is displayed here. And next we copy the third function, that is the lower limit. That function acts as the lower limit for the given function. And just type it G3, we get G3, but this is an error in copying, error occurred in copying. Then purple is the color, so purple is retyped. Instead of using that quotation along with the name of the color, instead of using that, we just type it, and if you want to see the output, you just you just type G3 again, and you can take the output. You have to wait for the output. See, with this we have obtained that output. That is the upper curve, and the lower curve is this one in green color, and red color is the actual curve whose limit we want to find at the given point, the specified point. Now we are trying to combine the three curves, combine the figures of the three curves. How can we do that? For combining all the three, because in G1 contains first function, and G2 contains the second function, and G3 contains the third function. So we want to combine all the three figures. You can do that by typing G1 plus G2 plus G3, and you know G1 plus G2 plus G3, since G3 can give you the combined effect of the three functions. Yeah, that is available. That we have obtained that combined effect. You can see that, and both the three curves are drawn together in a single figure, and you can see the curve of the function cos x by x. The curve of the function cos x divided by x is always in between the upper curve. Upper curve is 1 by modulus of x, and the lower curve is the upper curve is 1 by modulus of x, and the lower curve is minus 1 by modulus of x. So these two curves have opposite signs, and these two functions have opposite signs. So and that the given function is cos x by x, and that is clearly between both functions, and you can see that as we proceed from the starting point from the value of x equal to some x equal to 0. So as we proceed from the value from the point x equal to 0, from the point having the value x value 0, and up to if we proceed by considering points one by one, and if we move to infinity, then you can see that the first function reduces its value from a higher positive value to 0 gradually, continuously, as it goes to infinity. As the change applied in the value of x goes to infinity, then you can see that the upper curve reduces its value, and it comes closer and closer to the point 0, or the function value 0. And you can similarly you can consider the lower curve, that is the third function, and the curve representing the third function, and you can see that its value is gradually increasing and coming closer and closer to the value plus closer and closer to the value 0. So the functions or both curves approaches 0, one at the upper level, and there's another one at the bottom, at the lower level. And then as a result, and since the function cos x by x, since the function cos x by x is squeezed by these two functions, the first and the third function, since it is squeezed by the first and the second first and the third function, and both of these functions goes to 0, changes its value to 0 as x approaches infinity, then we have to say that by using the squeeze theorem, we have to say that the limit of the given function, that is cos x by x here, the limit of the given function is approaching 0. Cos x by x is the limit, is the given function, and the limit of the given function it is coming to 0. You can see this red curve is always, it is enclosed by, it is bounded by the purple colored curve and the green colored curve. Purple colored curve at the upper portion, and green colored curve at the lower level. So its limit tends to 0. Limit of the given function tends to 0, and this information we can elicit from this discussion. Okay, then coming, see, you can see that figure here given, and okay, now you can apply the same method to evaluate another limit. It's the limit of another function. So consider the problem limit. Find limit of limit as x tends to 1 plus, limit as x tends to 1 plus of the function 1 by natural logarithm of x minus 1 by x minus 1. So for that you can write limit, the function, the command limit, then in bracket 1 divided by log x minus second part is the second part of the function is 1 by x minus 1, and then you put comma and x equal to 1. Where do we want to find the limit? At the point x equal to 1 we want to find the limit, so we write x equal to 1. After that you have to specify the direction, because we want the right limit actually, that is clear from the symbol x tends to 1 plus. So we want to evaluate the right hand side limit. Okay, therefore you should write the direction. For direction you should write plus. yeah, the positive side, plus means the positive side, so you must fill you must substitute direction dir equal to plus in quotation. Okay, so let's try this. We are going to typeset that in the system, in the Jupyter notebook, and then you just replace that, you put quotation, and then you can okay, direction is plus, you can type plus. After that you can close, no, okay, and that single quotation is already there. Okay, inside that okay, put the quotation, then plus plus. Okay, yeah, we have obtained that limit of the function, or more correctly, it is the right limit, right hand side limit. It is 1/2. Limit is obtained, is calculated by the Sagemath system, and it is displayed equal to 1/2. And if you want to draw the plot of the curve, you can just use this command. You can use that in instruction part. But see, yeah, okay, g equal to plot. We write g equal to plot, then in bracket it's plot, and then in bracket 1 divided by logarithm of log x must be there. So okay, and that is in bracket 1 divided by 1 by log x minus 1 by x minus 1 in bracket, and then comma x. The range is specified from 0 to 1. It's a small range specified here, and then figure size is given equal to 3. So there is a very rare chance for an error in that, in the statement type return. And now I am going to take the output. Okay, wait for the output. Let's wait for the output. Okay, it's taking more time. Okay, why? Oh, sorry. This is but no, we want to type G also, and that was not written there. That's why that output is not coming. Okay, now it's corrected. Yeah, that output it's now available. Yeah, output is obtained as a curve. You can see that the limit, you can verify whether the limit is correct, the calculated limit is correct. Okay, thank you.